In Chapter 13, we're going to be locating restriction sites by finding palindromic sequences. And it's going to give us a chance to explore more about using, testing, and sharing code. So I always like to start off with the Rosalind definition here. And there's some really fascinating background on why this is important to find palindromic sequences. But what we're trying to do is pretty simple. Here it shows that the DNA string is a reverse palindrome if it's equal to its reverse complement. So it shows here an example sequence is GCATGC. And it shows why, and then it further shows that given a FASTA file with a sequence like this, that there are several reverse palindromes, and we're only looking for ones that have a length between 4 and 12, so that's actually going to be a hard-coded part of our script. And so we just have to go through this string here, find every sequence of 4 that is equal to its reverse complement. So how will we do that? Well, we've already seen that we can use the BioPython, the seek module, to find reverse complements of sequences. So to get started, let's just go into the top level directory, and I'm going to source the VNV bin activate. I'm going to do that in 2 windows. And then I'm going to go into the 13 REVP directory, and we see that there are a couple of solutions here already. And I'm going to start off by importing, by going into a REPL, and then I'm going to just look at this sequence, this code right here real quick. So I'm going to import seek. I'm going to set seek equal to the example sequence that was given to us on the Rosalind page. And then I'm going to look at the reverse complement of the sequence, and we see that it is in fact the same. And I can even write a little test here that the reverse complement of the sequence is equal to the sequence. So that is what we're going to need to do, run through all of the sequences in a given sequence, all of the subsequences that are between 4 and 12 base pair long. And this is going to give us a chance to explore some more functional programming with map. We haven't used zip, I don't think, yet, and enumerate we've used a few times. And so we will learn how to find reverse palindromes, how to create modules to share common functions, because we will see that we are reusing several functions from previous exercises. And it'll give us a moment to talk about the Python path environment variable. So to get started, let's just play around with one of the examples that we have, one of the solutions. I'm going to copy solution 1 to, it's called, should be called revp.py. And if we look at the help for this, you see it's pretty straightforward. It's just going to accept a single input FASTA file, and that is all. And then we will be reading that with the seek.io module as normal. And let's look at one of our test inputs. This is the same example as from the Rosalind page. And so given this sequence, we are going to be looking to create this sample output for 6. So this is saying that there is, at position 4, a 6mer that is a palindrome. So we're going to create this output, and it doesn't matter actually the order of the lines of output. So we'll have to take that into account in our testing. So if we run our RevP on test inputs 1, then we see 5, 4, 7, 4. Let's see, 5, 4, 7, 4. You see they're out of order. Doesn't really matter. There's the 4, 6, and there's the 6, 6. And there's the 6, 6. So it doesn't matter the order. We'll take that into account. So how do we write that program? Here is a visual example of the locations and the strings that we're finding here. So starting at 4, going 6 base pair, we see that this ATG, CAT, that is a reverse palindrome. Then there's a 4mer starting at 5, going to 8. There's another one here starting at 6, going to 11, and on all the way down here. And so let's write that program. So starting over from scratch, I'm going to use a little new py action here. I'm going to overwrite that, and then at this point I think you probably know exactly how to get started here. Probably I'm calling this file here. I don't remember exactly what I called it, but I'm going to go down here. I'm going to select the file bit. I'm going to change this from an optional argument to a required positional argument. This will be the input FASTA file. It is going to be a file. It is going to be a readable text file, and it is going to be required because it is positional. And then we will just have the one argument. And to get started, I'm just going to print the file name. So print args.file.name. And I believe that is what I called everything in the original. Yes, just file. And I'm suggesting that we just print the file name. So to get started, let me just, sorry about that. Let me just open a third window here. I'll go into my top level directory here, bin activate. Then I'll go into here. That way I can run revp with test inputs 1. And I'm printing the file name. And if further I were to run pytest at this point, I should pass at least a few tests because the program exists with the correct name, it does print a usage, and it rejects a bad file. And again, I will record a video at the end explaining how to get around the use of the deprecated argparse file type. But all the tests are written and the book is written around that, which was not deprecated at the time. And so I'm just going to continue using it because it does continue to work. So we need to open our input file here and get a sequence out of it. And I'm going to use seek.io for that. And so I already have a window open here, a REPL. So I'm going to go over here and import seek.io. And let's just talk about real quick the seek.io parse. That will parse. It needs an open file handle here, and then it needs to know the format of the data that it's reading. And I have shown you a couple times here that I can put that into a variable. I can put the whole seek.io parse into a variable. And what is the type of that variable? Well, it is this iterator. So it hasn't actually read the entire FASTA file, which would be terrible because if it was a very large file, it could soak up all the memory on our machine. It's actually just something that will generate the records as we want them. And because it's an iterator, it's of the class of iterators, there's a function that I can call on it called next that will force it to produce the next record. And I used this in one of the exercises where there was only one record in the input file, and so I read it, I forced it out by calling next on records, and I got rec. And if we look at this, we see here I get the string representation for the object, the seek.rec object that we have in there. And I can further, I can just force out the sequence part of the record, and I will stick it into seek, and I will stringify it, forcing it to tell me instead of it being this seek object that wraps around this string, it's just going to just be the literal string. And I just want to point out that when you're working with iterators, if you were, for instance, to open the seek.io parse on an empty file, and now I've included one here for your testing, I will say empty is equal to that, and then if I try to get the next record out, it's actually going to raise an exception. It's going to raise a stop iteration. And what happens when you're running a for loop is that when it hits that stop iteration, it simply stops going through the for loop. And so this is interesting code, and it can work under certain circumstances. If you know, for instance, there is at least one record in your file, but you do run the risk of raising an exception. And this is probably not very safe code to put into a script, but it's fine to be for playing around with in the REPL. So just a little side note there about how iterations raise an exception to say that they've exhausted there are no more records to return. So I need to find all the sequences that are 4, 5, 6, 7, up to 12 base pair long, and that is exactly what k-mers are. And we've done this several times, so let's just into our REPL, let's just define this function. The number of k-mers is equal to the length of the sequence minus k plus 1, and then therefore if n is less than 1, then we're going to return the empty list. Otherwise, we're going to go through this list comprehension to return all of the sequences. And so with that, I now have my find k-mers, and I can do, for instance, find k-mers in my sequence that are 4 base pair long. And I actually just noticed something here. I called my variable seek in the top level here, but inside of my definition here of my function, I've also called it seek here. And it's important to note that this seek only has scope inside of this function. So my regular seek continues to be this longer one, even though I passed it into this other function here. This seek is a completely different seek. And it only exists during the lifetime of the execution of the function. If you're not familiar with scope in different languages, Python's is a little different, especially when you get into longer programs. You can have these things called global variables, which some programming languages don't allow. So with that, I can actually go through the range of k-mers that I'm supposed to get, which is between 4 and 12, and the upper range here for the upper number in range is not inclusive, so I need to go to 13 to get 12. And let's see how many k-mers there are to look at for each one of those lengths. So when I'm looking at 4-mers, I'm going to have to inspect 22 k-mers. And when I'm looking at 5-mers, there'll be 21, and it drops down by 1 each time, which makes a lot of sense. So that is basically what we need to do, and probably some of you have already seen the answer, and I would highly encourage you to stop the video and go write your own solution for this. So how do we find reverse complements? Well, we spent all of chapter 3 on that. And there were a lot of little clever solutions, but by far the easiest is to use bioseek reverse complement, and so I'm just going to use that. And we can start off by finding all the 12-mers. So let's just look at those, the longest ones. There will be fewer to look at. So in my REPL here, I'm going to find all the 12-mers for using k-mers. And let's look at those. What do those look like? K-mers looks like that. Let's see, how many do we have? We have 14 k-mers that we want to look at. I've already imported my seek here, and so I can actually use a list comprehension here to come up with all of the reverse complements of those k-mers, and I can put them into another variable called revc for reverse complements, and I can see how many of those are. Revc, there are 14. So that is one way to create a list of all the reverse complements. Another way would be to use a map. It's exactly the same result, and I actually usually prefer to use a map. I feel like it's a slightly less typing. I don't need to create an actual lambda here in the map because the seek reverse complement expects just exactly one argument. So without the lambda, the k-mer will be passed in directly to reverse complement, and if we look at that, I get the same list of reverse complemented sequences. So a couple of different ways of finding those. So now that I have both, I can iterate over all the different lengths, and I can find all the k-mers, and I can find all the reverse complements. You simply need to run through those lists and find where the sequence is equal to its reverse complement. So definitely encourage you to go ahead, charge ahead, and do that. I'm going to keep talking here to tell you that my solution is going to use zip, which apparently I did bring it in chapter 6, and that's going to create pairs. So let me show you how I go about doing that. So given this sequence here, we'll just take one of those sequences. This is probably the same sequence that we started off with. Let's find all the k-mers, and let's look at those real quick. So I like to, the reason I'm working here in the REPL is so that I can actually look at the answers here and think about what I'm doing along the way. So here are all my formers. And I can create the rev complement by using that same map statement there, and I've got all my rev C. And now what I'd like to do is create the pairs of them so that this TCAA is paired up with TTGA, and then CAAT is paired up with ATTG, and on down. And then I can look to see where these are the same. And I can do that with zip. So let's look at zip real quick. If I do this, you see it's going to give me a zip object. So I need to use a list, the list function to coerce that into a list. And you know, I'm going to from pprint import pprint. That way I can pprint this data structure. Let's see if it looks prettier. Yes, that looks much prettier. Now it's very easy for me to see that it is a list of tuples, and the tuples are the values from k-mer, the first value from k-mer paired with the first value from rev C, the second one from k-mer, this paired with the second one from rev C, and all the way down. And if you'll remember, zip will only zip to the shortest list. In this case, they are the equal in length, of course, because they are just one is a transformation of the other. But we talked about in that chapter where we first introduced zip that there's also the zip longest function that you might need to use at some points. So with that, I can assign that to a variable that I'm calling pairs, and I would like to point out that in this instance, the length of pairs is 22. It has actually created that list because I have forced it into a list. But if I had wanted to, I could have assigned pairs to be just the zip operation. And again, pairs now would be this zip operator, and I could then, for instance, use next on it repeatedly to get the next versions of the next records out of the pairs. And that would be important if we were looking at some really, really large input and we didn't want to first copy in all of the k-mers, which could be, you know, perhaps millions of k-mers, and then we make a separate parallel list of perhaps millions of reverse complemented strings, and then we make a third copy where we actually copy both of those lists into a new list that has tuples. And so now we've essentially, you know, quadrupled the amount of memory that we're using to represent this. We could use lazy operators to represent all of these as generators, as iterators that would produce these lists as we need. So we're using very small data sets here, and we're just getting used to functions, using functions like map and zip. But it is important to realize that you could end up using prodigious amounts of memory if you're using very large inputs. So with that caveat, there's one more piece of information that I need to know, which is the position where these pairs occur. And we can get that from enumerate. So in this final form here, I'm showing that what I want to do is, let's go back and reassign pairs to be the list of that so that this code will work. So now I have all of the positions and the tuples where they are. Now, one thing that's off here is that these are, of course, zero-based, and pretty much all of the Rosalind exercises expect the positions to be one-based. And I haven't used it much in this book, and I kind of regret this, but there is a second argument to enumerate, which is the start value, where I can say start counting at 1, and I can even shorten that to just be 1, and it will start counting at 1. So I'm going to incorporate that into one of my solutions here so I don't have to correct it by adding 1 to the position. So that's really handy to know about the enumerate function. So let's talk about that. Now, looking at the list I have highlighted here in the book, we can see that at position 4, they're the same. At position 6, they're the same. And then 16, 17, and 20. So I have here a piece of code that will go through, it will enumerate the pairs. And so pairs is then going to be the position, sometimes I call that I, and then the pair. And pair here is going to be a tuple. And so to talk about the first member of the pair, I'm going to subscript it with 0, and the second one is going to be at subscript 1. And so here I'm using a list comprehension with a guard, which is very, very cool. So if the first member of the pair is equal to the second member of the pair when I enumerate through them, I'm going to print out the position plus 1, because here I've just used the regular old enumerate and it's going to start counting at 0. So let's look at that in the REPL. So we have 5, 7, 17, 18, 21. And those are the correct positions that we expect. And let's just talk about how I could have used the, I'll put here start is equal to 1. And so therefore I would not need to correct here. Position for position gives me the same answer. And again, remembering here that what's going on here is that enumerate is returning itself a tuple of the position and then the values that it's returning, and those values are themselves tuples. So tuples can contain within themselves other tuples, any other data structure. And in chapter 11, I talked about these little helper functions that I picked up from Haskell that I enjoyed, FST and SND for first and second, for dealing with tuples to get the first and the second values out. And I don't really like subscripting here. I think that I can write that much more prettily. And so I would like to bring in those functions. And so in this exercise, I thought, well, this could be an interesting case to talk about how to write code so that it can be shared. And so here I have this I hesitate to call it a Python script. It's really a module of code, and all that makes it a module is just that it's a common.py. I put the py extension on it so that Python would know to look at this. And one of the first things that hopefully you notice here at the top, there's no shebang line. This is not a script. There is no main function. If I go down to the bottom here, there's not that couplet that we see at the bottom of every program here, this if name equals main, then execute main. This code is not intended to be executed as a script. It is simply a file that contains function definitions that I can use. And in addition, it contains tests. So I talked about this FST function, and I'm using some typing here. I say that it accepts a tuple that can have any data type in either position, and it's going to return therefore any data type because it's going to return what's in the first slot. And you see here it just returns to subscript 0. And I have a couple tests here where I have 1 and A, and when I ask for the first I should get 1, and then I reverse those. When I have A and 1 I should get A. And I have the second for the second function with a little test here for it. And then I've put in here find k-mers, so I don't have to go through the pain of typing those in every time. Now I'm just putting it into a common file here, and I'm just calling it common because that's something that kind of makes sense. But as your programs grow and as you write more code, you might find yourself creating several little modules with common bits of code, and so you want to call them something that makes it easy to remember how these functions are kind of grouped together as things that make sense together. So what's cool is that I can even run PyTest on my common module, and because there are functions in there with tests to go with them, let's run it with -v. And we see here it's running the 3 tests that I wrote, and so I can have some confidence that these little functions, they're very simple and they're tested, and so I can have some confidence that I can bring these into my larger program and rely on them and build up more elegant and easier to read programs with them. So if I right now in my REPL here that I've got, I can bring these in because I'm in the directory where common is located. When I tell Python from common import these 2 functions, it is smart enough to say, well, let me just look for common.py in this directory, and indeed it finds it. And now I can call, first on a tuple that has, let's put a and 1, and it returns a, and if I call second on that, it returns 1. So that works, and it's a really elegant, nice way to share code, and so it makes this list comprehension, I believe, much easier to read. Now I can call first on the pair if the first on the pair is equal to second of the pair, and that for some reason just reads better to me. I think it's easier for me to understand. So with that, the other thing to understand here is this thing called Python path. There's this other thing in your environment called path. We haven't really talked about it much. I have an appendix that really goes into trying to explain path, and it's a very important concept to understand when you're working on Unix systems. And so there's an additional one for Python called Python path. It works exactly the same. It's just a list of directories where Python will look for modules. So when you say import some module, if you do a pip install, it goes into these standard directories where Python knows to look. Well, a lot of times you don't have access to write to those directories, and so you could create, for instance, in your home a .local, and I like to put .local so that it's a hidden directory and I don't have to see it when I do an ls at my home directory. So inside my local directory, I can have lib, I can have bin, I can have a lot of, if we look here, what's in my .local directory, I have bin, lib, share state. There's a bunch of programs in there, a bunch of code, our studio, and there's a lot of stuff for virtual environments, and just all kind of stuff is shoved into there. So that could be a place where you share your own Python modules and you put them in there for yourself, and especially if you're working on like an HPC and that's a shared file system across your different nodes, that could be a way for you to easily share code with yourself and your different projects. So here is how I incorporate those ideas into my first solution, and I think it's probably at this point we'll just look at, I'm going to copy solution 1 to REVP, and let's look at REVP. I have, here we go, already had it open here, and so I'll look at it here in the PDF. I feel like it's a little easier. So for each record in seek.io, there could be several in this file, we're going to read one record at a time, and then we're going to get for each of the values of the Kamer sizes from 4 to 13, which is actually 12. We're going to find all the Kamers, then we're going to find all the reverse complements of those Kamers, then we're going to enumerate over a zipped up version of the Kamers and the reverse complements into position pair, and if the first is equal to the second, we're going to print that. So here I'm not doing, I could do all of that work together with a guard. I decided here it might just be a little easier to read if I wrote it out as an if statement. So this is one way to go about writing this, and let's execute this. So if I run REVP on test inputs 1, it works. So let's look at 2. There's quite a bit more output. So let's just run make test. Make sure that it passes all of our tests, and that works just fine. I would like to point out that if I wanted, I could enumerate starting at 1, and then I would not need to do position +1, and I make that change, and then I go run make test, and I see indeed that passes. And that is the whole point of having a test suite, is that I can look at my code and say, oh, I think I found a cleverer way to write that, and then I go make a change, and then I run my test, and I'm like, yes, that works just as well. So however you want to write that is fine. And probably if you went off on your own, you probably came up with a different version of writing it, but as long as it passes. So the first and second functions are fun to use and are really wanted to show, you know, how you can write modules and share functions and stuff. There's really some work I'm doing here by writing all this code and not just using operator equal. We've talked about the operator module in chapter 6, and there we use the not equal NE function and LE. And we've also talked about add functions. Here, if we look here, I can replace that, the line here, if first is equal to second. Well, that is operator equal. And this is probably, this is kind of an awkward way to write it, but I introduce it this way because of what I want to show you here. So let's say that my pair, let's see, do I still have pairs here? So let's just assign this as pair for the first pair. Let's just say we have this pair, and I'm going to import operator, and I'm going to say operator EQ, and what it wants is, well, let's just look real quick at help for operator, and it wants an A and a B, and so we need to pass in two values. And so if I try to say operator EQ on pair, that's not going to work. It says it expects two arguments, but it got one because pair is technically one argument. So I can, though, let's see if we do this in, yes, I can't splat this in the REPL. I could show it this way. If I try to print pair, then it's going to print the tuple, but if I print the splat, then it's going to expand the tuple into its constituent values and make it into a list, and then when I feed a list to print, it's going to put the new line, a space in between each of the arguments. So we've seen here what splatting does. It kind of explodes the underlying variable. So therefore, if I go back and I run operator equal on splat pair, then it's false. But if I were to change pair to, let's say pair is equal to, AAAA and AAAA, and then I run that is true. So I'm showing it here that I could rewrite part of that using operator equal pair like that. And here what I get into, going back to this list comprehension, that I could write this a different way. So let's let me close my editor here. Let's copy solution 2 using an if statement here. Let's look at what that looks like, REVP. That here I'm using the if statement here with operator equal pair. So what I've changed here is that I brought in the operator module, and then I'm changing really just that one line. And let's verify that makes sense. Let's make test. That works just fine. But there's this other version. Let's copy solution 2 using a list comprehension to REVP and look at how that one looks. Here I've gone back to the list comprehension, and here, because I want to use this in the guard, I feel like that actually, to me, that reads a little better. And here I am essentially, I'm just writing it with a list comprehension and then a for loop over that, and I can run make test, and that also works just fine. So a couple different ways of writing that, and I think that understanding how you can bring in the operators to write functional versions of the operations, I think that's actually kind of clever and interesting. So I think at this point, one of the things that bothers me about this solution is that there's some work going on here in this for loop that could really be pulled out into a function and then have a test for it. And in this case, it's one more instance of me showing you this, and it's really overkill because we already have tests for this, but it's because this is the only thing the program is doing. And in a real program that you're going to go off and write, this will be just one tiny aspect of a much larger program that you're writing. And so you're going to need to think about, like, how can I isolate this one function, this one bit of code, this algorithm, into a function that I can understand and document and test. And so let's just go ahead and go a little further and turn this into a function. So the way I would start off is by defining my function and thinking about the types that it's going to take. It's going to take a sequence, which should be a string. It's not going to be a seek IO, a seek object, and it's going to take a size for k. And that is going to return a list of integers, which are going to be the positions in that sequence of the reverse palindromes. That's what REVP is, reverse palindrome. And to start off, I'm going to say that it's going to return the empty list. And that way, the reason for doing that is just to get something in place that compiles, that is syntactically correct, and then I can write a test for this. And so this seems, obvious to me, but I have had arguments with people that in order to write a test, you actually have to pass it in things that you know the answer to, and then you have to get the correct answer back. That seems obvious, but trust me, some people don't seem to believe that. So I start off here by using this sequence that I know. I can manually verify that the reverse palindromes that are 4 base pair in length can be found at positions 3 and 5. But when I go up to a Kmer size of 5, it should return nothing. When I go to 6, it should return 2 and 4, and on up the ladder here. And so I've written several tests, so enough to make me feel like this works. And when I put this into my code, like let's just say, for instance, I take this bit of code and I want to add it to this version of my program here. Oops. And it really bothers me not to have that separator there. And then let me take these tests, and it never transfers well from the PDF, but that's okay. And let's just say we have now added this skeleton of a function and a test for it, and so therefore if I run PyTest on my REVP function, and I'll run it with verbose. Oh, list is not defined. That's fine. We'll go up here and import list. Let's see if we need anything else. Now we see here I am failing my REVP test because I should be failing because I'm always returning an empty list. And so then we go and we say, okay, well, I'm going to take all of the code, all the relevant code that belongs in there, and I can just take here these 4 lines. These 4 lines that I've been playing with in other contexts. Let's just paste those in there. Indent them. So I'm finding the Kmers, I'm finding the reverse complements, I get the pairs, and then I have my list comprehension here. And now all of this is tucked away in a nice little function. Let me save my code, and now let me run my test. I'm now passing my test. And so that means that my the main code, the main function now becomes quite a bit nicer. I can go here and so now my main function becomes quite a bit shorter. So for k in my Kmer range, I can say for the position that is found in the reverse REVP, excuse me. I just need to print the position and the kmer size, which is what I was supposed to be printing all along. And so let's just run this. It's called REVP now. Let's run it with, test inputs 1. And I get the output that I expect. Let's run make test on this. And now my entire program works. So one of the things that's important to note here is that the function that I wrote, it does not print anything. That's a bad way. You cannot really test code that prints things. So the point of writing this REVP function is that it returns data that can be then tested like this. So it's up to really the main function. It's up to the kind of the user-facing code to actually do the printing. And the other code that I'm writing is just calculating on data and returning data. And that is the really, when you start getting into these libraries of code that just provide functions that give you access to these algorithms and don't do the printing, and you write user-facing code to do the printing and the writing to files and all of that stuff, that's when your code starts to get a lot more elegant and easier to maintain. So that's the whole point here of tucking this away into a little function. So with that, I do show here that in a very silly way, you can actually write list comprehensions within list comprehensions. I wrote this out just because it's possible, but I even can't follow this. I would not recommend you write code like that. Anyway, I did have this guy, Joe, that I worked with, and he said if it was hard to write, it should be hard to read. So that's actually terrible. It was a joke. So don't write code that's hard to read. All right. So let's take just a moment to talk about testing the program. I hope that you will get into writing your own tests. I hope that at this point I've proven the utility of doing so. And so I would like to point out that in my tests inputs directory, there's also these .out files, because the shorter inputs that they give you on the Rosalind page to demonstrate that when you go to actually solve the problems, the inputs get quite a bit larger, and so therefore the outputs can get a lot larger too. And so putting the expected strings into your test files can get really onerous. So let's look at the tests, the REVP test, and you'll notice here that I'm defining a couple of inputs. And there's an empty file here. I think it's important to test your programs with empty files. And we see here in PyTest land that I've defined my test with test underscore at the beginning of the names. These tests will be run in the order that they're defined in the file. So I have the simplest test first, and then it gets into actually running these tests. And so you notice here I've created a helper function called run. It does not start with test underscore. And so test OK1 is going to run with input 1, and then test OK2 is going to call run with input 2, and then there's one for empty. And then I have some other helper functions down here, random string for generating, like a bad file name. So what does run do? Well, it says that there's going to be this expected file that is the file name plus .out. And we see that in the inputs directory that for 1.fa, there's also a 1.fa out. And this works just fine because I wrote the test and I put the files in place. And so I know that this is not going to fail. I do go to the trouble of asserting that the expected file does actually exist. That's one of the tests. And then I run my program using the input file that's given. I verify that the return value is equal to 0, meaning that the program ran correctly. And now I have the output from the program, which could be a very long list of lines. And so I'm going to actually turn those, I'm going to take the output, split them on lines, and turn them into a set. So I can compare a set of lines to another set of lines, and it doesn't matter what order they were defined in. It will evaluate to the same data structure. And then so I just do the same thing. I open the expected file, I read it, and I split the lines, and then I put that whole thing into a set to make the lines unique. and it doesn't matter the order, so then I had this expected value, and then I just assert that the two sets are equal to each other. So there's a couple interesting things here. One is that this is how I get around the fact that the lines could be in different orders. I found in my testing that they could come out in different orders, and it wasn't exactly the same as Rosalind. So this is how I got around that problem, and also how I get around the fact that if we go into the test inputs and we look at the number of lines here, the 2 input has 16 lines of input, but it has 70 lines of output. And if we look at 2.fa.out, this would be kind of a bear to put into as a list of strings. If I were to want to stick this into my test file, that would just be ugly. It would be just this huge long list of strings that I could just read from a file. This is a much better way, in my opinion, of writing the tests and having the inputs and outputs there. It's a little trick that I use quite a bit also in Rust as well. So that's what's going on in the tests, and using these little helper functions, it makes the test file also easier to read. So going further, I recommend that you could, for instance, change the minimum and maximum values to be from hard-coded values to be command line parameters, and then therefore you will need to add additional tests and add additional input files and the expected output files, and so figure out how to do that. And then you can also look for regular English palindromes and just start searching through. You can go download books out of Gutenberg, Project Gutenberg, and search for palindromes. You can stress yourself to find very large corpuses of text to play with. And then make GitHub repositories and put documentation in there. Learn how to write a README. Learn how to create a GitHub repo and then share it, and realize how much fun it is to share your code with the world. And you start small, and then one day you create something amazing that other people really find useful, and that's quite fun. So a couple of review points here, that a big part of what I was trying to get you to think about was reusing functions, because we keep coming back to some of these same ideas, like finding k-mers, that we put them into a common module. In this instance, it was just in our same directory that we were working with, but we keep using that. Maybe we would want to create one shared directory that we could use amongst all of our programs, and maybe even it wouldn't even be in this project directory. Maybe it would be in our .locallib Python directory, and we would expand our Python path to include that directory, so that in the future we don't have to keep